Do you see my?
Yes, I
Okay,
can see.
right. Okay, so for today we will continue the lesson 5 on training neural network. Right. On the previous lesson, we study about how to use a batch normalization, how to do data pre-processing, and how to use activation function in order to optimize the training of neural network, right? For today, we will study other things that might affect the performance of neural network. So here's the outline for today. We will discuss about the optimization algorithm, and then about the learning rate schedule, and then the anti-overfitting techniques, and then data augmentation, choosing hyperparameter, and then the ensemble method to combine multiple model, right? And then the last thing we will discuss is about transfer learning. Okay, so first let's start with the optimization algorithm. Okay, so for the neural network, we already know that in order to train the neural network, we can use the stochastic gradient descent algorithm, right? And for that algorithm, the idea is to do in an iterate fashion, that you have a loop, and inside a loop you do the update for each step, right? And for each step you calculate the uh, gradient for the data gradient update for each weight, right? And then you uh, will update the weight with the step size multiplied with the weight gradient, right? Okay, so in that way, after a number of iteration, you expect that, I mean, the weight will converge to the, to the parameter that make the loss uh, to be the, the minimal, right? Okay, so now we discuss some problem with the stochastic gradient descent, right? So um, so assume that you have you have to update two weight, or you have multiple weight to update, right? Each weight will be uh, can be considered as the uh, dimension, right? Now let's assume that you have two dimensions, the W1 and W2 to update. And let me uh, okay, have the pen. Okay, and this is the weight W1, and this is the weight W2, right? Right. And remember that in the case you do the updation, you have to update both the two weight, right? And each weight will be updated with the this amount, right? Step size, the learning rate multiplied with the weight gradient. Okay. So what if the loss train quickly in one direction and slowly in another? For example, what happens if we have the in the beginning we are here, and now we have to update the weight, right? And somehow it go very slow into that direction, and it go very fast in the other direction, right? Let's say that it will update W1 very with a very small step, and update W2 in a big step, right? This is due to the uh, weight gradient, right? So in that case, you are seeing um, uh, it when, for example, if you are seeing this situation, it will think that the algorithm have very slow progress along the shallow dimension, and exist along the step direction, right? And for example, it's go like this, like this, like this, till the optimal point, right? Um, And so in this case, you might think that, I mean, the problem is the loss trending quickly in one direction and not on the other direction. So in this case, you are seeing that it will go a long way till the optimal point, right? Right. And what we need is to be able to make the movement going to that direction, right? If it goes this way, then it's the shortest way to go from the initial point to the optimal point, right? And for the problem we observe here, it will go this in this direction, and that will make it go a longer way till the optimal, right? And now for this, we have another problem with stochastic gradient descent. What if the loss function have a local minima or a saddle point? For example, this could be a local optima, right? And this is a saddle point, right? And at that local optimal and saddle point, right? What do we have at this point? How about the gradient at this point? Can you tell me what is the gradient at this point?
0, I guess.
Yes, 0. Yes, because you are at the local minima, right? So in that case, for example, when you using that formula to update the weight, and that part becomes 0, and so you see no update for the weight, and so that's might cause a problem to make the algorithm stuck at that point, right? And you cannot, I mean, fine tuning the weight, and then it stop at there and going nowhere, right? And okay, so here we have the third problem with stochastic gradient descent. When you do the stochastic gradient descent, I mean, you may do the update with the minibatch, right? And then you have a minibatch gradient descent. So the update is not calculated by the mean of the error of every sample, but you do the error, the loss for that minibatch. And because you're using only the loss for that minibatch, a small number of sample, and so that you do the update of the entire weight for that by that loss. And in that case, of course, it might cause the path of the movement will be a little bit jittering like this, right? And it have no it don't go to the like the fastest in the fastest path, right? It goes jittering a little bit because you use you don't use all of the information to update the weight, right? And if you see the loss, if you plot the loss during the training, this is the number of steps, for example, and this is the loss, and you might see the loss will be like this, right? I mean, it have the trend to be smaller over time, but I mean, if you jump closely to the loss, it can be like this, up and down, up and down, up and down. But the overall trending is getting smaller, right? So do I need to discuss more about this? Okay, so there's something I want to discuss here is about the Hessian matrix. So the Hessian is actually a square matrix of second order partial derivative, right? It's not third order, but it's second order, right? You can check the internet about this. So actually, if you know about the Hessian matrix, you know what is the optimal point in that, space, right? So here is that the fact that's saying the fact that the loss function have a high condition number, the ratio of largest to smallest singular value of the Hessian matrix is lag. So that means that the partial derivative over different dimension will be very different. Some is small and some is big, right? That's why you are seeing this problem. The loss will change quickly in one direction and maybe slowly on the other. Okay, so now we will discuss some extension or some kind of optimization mechanism that we can use to to somehow make the algorithm work better during the training, right? We don't want it going that way because it's going not the fastest path, right? We want somehow the optimization when going this way, all way to the optimal direction with the shortest path as the short path as possible, right? Okay, so now we discuss one optimization. It's SCD plus momentum, right? So this is a vanilla stochastic gradient descent. You update the weight as the next time step equal to weight at this current step, and then plus the learning rate, and then the delta gradient, right? And you do it in a loop. And for stochastic gradient descent plus momentum, you have a small thing called the velocity, and this is a formulation for the SCD plus momentum. So now you have that velocity Vt, right? The Vt in the next step equal to the Vt in the current step plus that delta gradient, and then you update the weight by the current weight, and then the learning rate multiplied with that velocity, right? So by using that formulation, right, it means that you want the gradient to continue moving in the zero direction at the previous iteration because you have that velocity amount, right? And this velocity is actually built at the running mean of gradient. You are seeing that the velocity is like the running mean of the gradient. Right? You calculate the velocity by the velocity in the previous step, and then plus the amount of the delta gradient, right? And you have that parameter is like the friction, right? It's like when you're moving, you get the like you are in the physical work when you have a car that's moving on the street, right? And actually you have the friction that somehow reduce the speed of the car. In the meantime, right? You can configure the friction at the beginning to be a lower value due to the fact that you are not aware of the right direction to go, right? For example, in the beginning, you can say that okay, the friction can be a small, so that that velocity will not be big, right? And then you have you give the gradient the trend to go explore a little bit in a different direction, right? And then in the next step, right, when after the initialization, you discover the right direction to go, and then in that case you can configure that friction to be that a big number, close to 1, for example, right? Here you have another alternative equivalent formulation for the SCD plus momentum. right? And this is a formulation we see in the previous slide. And now we can, in the previous slide, is it the right way? No, this is a formulation in the previous slide. And now you have an alternative equivalent formulation. So in the formulation, you have the Vt equal to, this is a friction Vt minus the learning rate and then the delta gradient, right? And then you update the weight with that velocity, right? The formulation is a little bit different, but they give the same sequence of x, right? You can try to test with the t equal to 0 and see. I mean, they will give you the same sequence of x, right? And now, if we use the SCD plus the momentum, you are seeing that if the gradient is somewhere here, right? And the current gradient is 0, but you still have the momentum to go into that direction, right? And even now, even for the center point position, you are going into that direction, right? Even at that position, the gradient equal to 0, but you still have the momentum to move further, right? So that you have the power to move on, right? And in the case of jittering, right, the updating of the weight will be slow on one direction and later in the other direction. You might see that if we use the momentum, then somehow we will let the movement of the gradient to be that way. So it keeps going into the right direction, right? Is there any question for this point? Is there any question? Hello.
I think no questions yet.
Okay, then we can continue, right? Now we discuss the next step of momentum, right? So, for example, in the SCD plus momentum update, this is the gradient, the current gradient direction, and this is the velocity direction, right? If you do the SCD plus momentum, then the actual direction will be this direction, the actual step, right? If we don't use the momentum, then if gradient this way, you go this way. If gradient that way, you go that way, right? Using the velocity, you can combine the gradient and the velocity, and the gradient will go to that way, right? So for next step of momentum, you also do the combination of the velocity and the gradient, but the difference is I mean the location of the head. Now, uh, for the SCD plus momentum, you do the combination at the starting point of the gradient, right? And for the next step of momentum, you do the look ahead to the point where the updating using the velocity could take, right? You compute the gradient there and mix it with the velocity to get the actual update direction. So now instead of, do the combination of that, initial step, that you do the combination of the head of the velocity direction, and then you have that net type of momentum. This is actual step direction. So by the formulation of the next step of momentum, you have the Vt at this the next step equal to friction Vt minus alpha delta F, right? and this is f the function of t plus p vt. So that's amount saying that you want to do to update to do the gradient at that, I mean, that point, right? And for the SCD plus momentum, you just do the gradient at that ht position, right? And this guy you do the gradient at the head of the velocity better, right? And now you do the same update, t plus 1 equal to t plus vt plus 1, right? And yes, okay. So so now we discuss a little bit about the formulation of Nesterov momentum, and for this you have that gradient of xt plus the friction vt, and usually this is a little bit annoying and you really want to do the update in terms of gradient of et, right? Now you can do the reformulation a little bit. You let this is xt how to say prime, no, not prime, xt something, right? And you let the xt something equal to xt plus friction vt, and then you rearrange a little bit of formulation, and then you end up with that I mean formulation to do the Nesterov momentum. So you do the compute the gradient x, right? And then you keep the old value of velocity, and then you calculate the new value for the velocity, and then you calculate the x. And in this case, you do the gradient at x, but you still have the Nesterov momentum update, right? So because we have no whiteboard in here, so it's hard for me to really write for you, but you can try to understand this. Let's try to reformulate the formulation a little bit, like you train or let ht something equal to ht plus friction vt, and now you replace this into that part, and you have a vt plus 1 equal to friction vt minus alpha delta f ht something, right? And now you try to reformulate the ht plus something equal to ht plus minus friction vt plus 1 plus this is friction, and then vt plus 1, and then you can you can have this formulation xt something, and xt something is actually here, right? Okay, so let's move on. So here is just a demonstration for the optimizer, different optimizers such as SCD, SCD plus momentum, and Nesterov momentum. So you see for the SCD, this is like the optimal point. We want to reach the optimal point here, and we started somewhere here in the loss plan, right? And now if we use the SCD, if we go, for example, very small step this way, right? And if we use the SCD momentum, we are seeing that if we go really fast to the optimization to the optimal point, and if we use a Nesterov, we have somehow having a better path, a shorter path to go to the optimal point, right? Okay, any question? Okay, so if you have no question, then we can continue. Okay, so now we discuss the ADA-GRAD optimizer, right? So for the ADA-GRAD, you actually add element-wise scaling of the gradient based on the historical sum of square in each direction. And by doing this, you have the effect of per parameter learning rate or adaptive learning rate for each weight, right? And what is the advantages of having adaptive learning rate for each weight? And you see that in the beginning when I discussed about the motivation and the problem with the SGD, right? Some weight will have a big update and some weight have a very small update, right? And that may due to the fact of that high conditional number in the lost plane, right? And if we use the same step size, same learning rate for every weight, then you see, I mean, the update step will be very different in each weight, right? Now we want the fact that we have a dynamic learning rate for different weight, so that if this weight is the delta gradient for this weight is so small, we can use larger learning rate, and if this delta gradient for this weight is so big, we can have small learning rate, right? So in that case, we have this formulation. So in order to update the weight, we have this is a constant learning rate we set in the beginning, and this is the amount to say that we have the dynamic adaptive learning rate, right? And this grade square equal to I mean the grade square in the previous step plus the square of gradient, right? So if gradient is too big, then we divide that I mean gradient with that bigger value, then we have smaller learning rate. So if we have grade square to be very small, then okay, that learning rate will be will not be reduced a small big amount, right? Okay, so now we see the demonstration with the ADA gradient. So if we have this updation scheme for the weight, then we will see that the update will the update in the stiff direction is damped, and the update in the flat direction is accelerated, right? If the leak is too big, then okay, it is that progress in that direction is down, right? The learning rate is getting smaller. If that gradient here is small, then we have the higher learning rate for updating the X. Is it clear? Hello. Okay, so let's continue. The second question: what happened to the step size over long time? What is this amount over long time?
I guess no.
Sorry?
Never mind.
Okay, so if we increase the learning step, then we are seeing that we will have, I mean, the learning rate to be very small, and then it will reduce to 0, right? Let me remove that. Wow. Okay. Okay, let's move on. Okay, so now we discuss the other optimizer. This is IMS Prof, or it have another name, Leaky Adagraph, right? So this is a formulation for Adagraph, right? You have this graph square, and then you do the updates of the weight like this, right? And we have the IMS Prof, and in the IMS Prof you have the decay rate that actually multiplied with the graph square, and then you have the 1 minus decay rate multiplied with the square dash, right? And if you for normally we recommend you to use the decay rate to be this value, right? And now we see the demonstration for the running of the optimizer. So this is a SCD. Again, it's not it's a worst case to use SCD to optimize the neural network. And now it's okay, we have the SCD plus the momentum. I see it's somehow going faster to the optimal point, but it's going a long way, right? And now if we see the visualization for the IMS probe, we are seeing that it's going this way, going fast and short way to the optimal point, right? You may see that this is thanks to the where you have adaptive learning rate for different weight, right? Any question? Okay, so I suggest that we take a 5-minute break and then we will continue. Okay, so let's continue our lesson. So I trained the slide a little bit to make it clearer for you to follow. So for example, in the case of Ara grass, right, when we I mean after a number of iteration over a long time, right, what the question is, what happened to the step size of a long time? I mean at the very late iteration, you are seeing that you have the great square equal to the great square in the previous step plus with the square of gradient, so that you see that the gradient square is always increasing, right? So if it is always increasing, then you have this part to getting bigger and bigger from time to time, right? And if this part getting to be bigger, then the learning rate divide to that big amount, and it will getting to be smaller. So in that case, you have the learning rate to be 0 after a very long time step. And you have the effect that the learning rate is always monotonically smaller, always getting smaller, right? And sometimes, I mean, that is like a sub-optimization you want to have, right? You want the learning rate to be getting smaller, and sometimes it's getting bigger if it's going to the right, to the wrong direction, right? And to modify the graph a little bit to get the optimizer smarter. For example, we have the RMS probe, and it's called leaky ADA graph. So in that case, we have the graph square equal to that formulation, and we have the decay rate. And this is like we have a moving average of square gradient, right? And by using that formulation, we don't have that, that parameter to be more monotonically increasing, right? And in that case, we have the update for the learning rate is not monotonically smaller. Sometimes it's getting smaller, and sometimes it's also getting bigger. So that's the idea about the RMS probe. Is that clearer a little bit? Any discussion? Hello. Okay, then I can move on.
I have a question.
Yes. Yes.
Why the decay rate is recommended to be 0.90, 0.99?
So the idea is you don't want that value to be very small, right? If you have, for example, in the case you have the inverse situation when you have the decay rate to be that 0.1, and if the decay rate to be 0.1, and somehow you have that part to be very small, and that part is close to the dx, right? Is it okay? Is that understandable? And somehow, if you have like this, then the graph square is affected strongly by the current gradient, right? And then you lost the momentum. I mean, that's the graph square equal to the graph square plus that current gradient square. You want to keep the momentum to go to the right direction, right? If you have that decay rate to be very small, then somehow the momentum, you use very little the momentum, and you follow the, you update strongly beyond the current gradient. Is that okay?
How about the middle value such as 0.5 or 0.6?
The middle value, I think that you may try, but this is the recommendation from practice, right? You can try. I mean, let user have a neural network, and then you try to use the RMS probe with different configuration of the decay rate, and you see which one is better. And by using a lot of practice, they have the recommendation for you that you might keep the decay rate to be this, I mean, big value, so that you can benefit from the momentum better.
Okay,
if you keep the very small, I mean, then you somehow you forget the past quite often, right? Okay, so this is a visualization for the running of a different optimizer. The case of SED is a case of SED plus momentum. It's going faster, but in a longer path. And for RMS probe, it's going in really the right direction to go. And the conversion is faster, the fastest one in this configuration. Okay, so now we discuss the ADAM optimizer. So this is a very popular optimizer we use nowadays, and it's like the default optimizer we use for training the neural network. And okay, so it's like this is like the simple ADAM optimizer. You calculate the first momentum and then the second momentum by this formulation. Beta 1, this is the hyperparameter, right? First momentum and then 1 minus beta 1 and then the gradient. So this is like the moving average, right, of the gradient, of square gradient, for example. And this is moving gradient of the gradient. And this is also the moving average of the gradient, right? And then you do the update of the weight equal to the weight of the previous step plus with the learning rate, and then you have the first moment and divide with the, I mean, square of the second moment, right? And it is that a number to make you not divide by 0, for example, right? Okay, so in the first impression, you can see it is almost like RMS probe with the momentum, right? And this is like the momentum, right? And this is an Anagrato RMS probe, right? So you multiply with, this is the first momentum, not multiply with the dx, right? In the update stream for the gradient descent or Anagrato, you multiply with the gradient here, and now you multiply with the momentum, and it's like Dressler probe with momentum, right? So here we have a small question about the first time step. What happened at the first time step? Can you think a little bit about what will happen in the first at the first time step? Can you elaborate a little bit on the answer for this question? Hello.
I think in the first step, the first and the second momentum only have the second part.
Yes, it have only the second part. And what happened for that? What will happen? And can you do the calculation for this part?
I think that the part will be close to 1 minus beta 1 divided by square root of 1 minus beta 2. So the dx here is not taken into account in the
Yes.
first time step.
Yeah, that's right. Okay. So usually we have this alarm in the full form. We have the first momentum and then the second momentum. We have the unbiased formulation. Let's say it's a bias correction. The first unbiased is first momentum divided by 1 minus beta t power t, for example, beta 1 power t, let's say. And then the second bias is second momentum divided by 1 minus beta 2 power t, right? And then it's a updation for the X, it is the RRAT or IMAX probe updation. So the bias correction here is for the fact that the first and second moment estimates start at 0. So it's make the algorithm more stable during the warm-up at the first few steps. So that's the idea about the bias correction in this point. So for the ADAM, usually you start with the beta equal to this value, 0.9, and this beta 2 is 0.999, and the learning rate exists on that, and they are the good default parameter for many models. So it's just a suggestion, right? You might try other configuration, but usually people start with the value, and they think it's a good default parameter for many model with the ADAM optimizer, right? Okay, so okay, so let's continue. Here we see the visual example of the learning rate process. So visual example of the learning rate process is we have SCD, we have momentum, and energy, other rad, other delta, and RSM prof. So you see that for the SCD, the thing we have here is somehow get stuck at the center point, right? And for the RMS prof, it's a black line. We see the RMS prof and diagram actually going quite in the right direction to go. We have the other delta, something that we can study further on. You see it's going very fast, right? If we use momentum alone, it's keep stuck a little bit because it keep going to that direction, explore that direction, and after quite a long time it will go to the other direction because it is due to the momentum, right, going to that direction, right? Okay, so here's another example of a visualization for different learning optimizer. Again, this is the SCB going very slow, right? And the IRS is the blue line here, and then the IMAT port is that black line here, right? And for the momentum, it goes to the other direction because this is the momentum. It keeps going that way, and then it takes quite a bit of time to change the direction to go back to the direction to the optimal point. Okay. Okay, so so that was about the discussion of different optimizer for training neural network. And now we discuss about the okay, so the next slide we will discuss about the second order optimizer. So in the first order optimizer, we use the first order derivation to calculate the direction to update the weight, right? And we update in an iteration fashion, right? Step by step, we're moving on, right? If we do second order optimization, we can use the Hessian matrix, and in the Hessian matrix, we actually have the information about different optimal point in that Hessian plane. And if we use the Hessian matrix, we can go directly from one point to the minimal point. But for using the second order optimization, we need to somehow calculate the Hessian matrix, and it's not simple to do, and somehow it really resource consuming to do this. For example, if you have to calculate the Hessian point, Hessian matrix, it have O n square element, and to invert the Hessian matrix, it takes O n power 3. So it's like a very costly to do. You can use some approximation to estimate that Hessian matrix. For example, the quasi-Newton algorithm, whatever. So I just put them here for you to to study at home or study further on, but it's not the focus point for this lesson for today. Yes, for example, you can use a limited memory DFZS version. So in this case, you don't need to store the full inverse Hessian matrix. And it is said that this algorithm usually work well in full batch and in deterministic mode, and it does not transfer very well to mini batch setting. And indeed, it is the setting we use the most common for training the neural network, right? Okay. Okay, so here's just to some summarization of different optimizer we can use. We can use an ADAM. It's actually the ADAM plus Nesterov accelerated gradient. This is something we see in that demonstration. Now, NIG optimizer. Or you can use RADAM. It's rectified version of ADAM. You can use local head and render, and they are something that you can study further on at home. Okay, so to sum up, in practice, the ADAM is a good default choice in many cases. It's often work okay even with constant learning rate, So SCD plus momentum can outperform ADAM in some situation, but it might require more tuning of the learning rate and schedule, right? And you may try the Gaussian schedule for finding the right learning rate, right? If you can afford to do full batch update, then you can try out the LBFGS. And don't forget to disable all the source of noise. This is a more, recommendation you can try. Okay, so the next part of the lesson will be about learning rate schedule. Do you have any question about the current part? Any question? Okay, so if you have no question, then I suggest that we take a 5-minute break and then we will continue. Okay, so let's continue. Okay, so now we study about the learning rate schedule, right? So for the learning rate, we can see that it is a hyperparameter for almost, common optimizer that we may use, such as stochastic gradient descent, stochastic gradient descent plus momentum, ADA-GRASS, mass probe, ADAM, right? So we always have the question, which one of the learning rate is best to use? For example, we can visualize the loss of different epoch learning step like in this figure we are having in here. And of course, we want to have the loss we reduce gradually, like in this, this line, the red line in here. So for this line is signify the good learning rate that we already use. If we have the yellow line in this curve, then it may signify that we have been using a very high learning rate, and for that we actually increasing the loss by we update the weight to be in wrong direction, that increase the loss. This might be due to the fact that we use a very high learning rate. Then for each step we going over the right direction, right? And if we having the curve like the blue line we have here, then you see that the loss reduce over time, but the amount of reduction is so small from step by step, right? It will take a long time to train the model, right? And if we have that green line here, we may see the loss reduce quickly in the beginning, and then it gets to be stationary at that value. In this case, it might be the problem of high learning rate, so that it can go fast to the right, to the region close to the optimum. But then because the learning rate is too high, then it can go to the right optimal. It go around and then it's stuck at that value, right? And what we have is that good line learning rate. And usually in practice, we usually start with lag value for the learning rate, and then we can decrease the learning rate over time, so that we have the effect that in the beginning we go big step, right? You go big step, and then when we close to the optimum value location, we can decrease the step, and then we go carefully so that we can reach to the optimum point, right? So we have several mechanisms to schedule the learning rate, and here we, for example, we can use the decay value to reduce the learning rate over time. Okay, so the idea is to reduce the learning rate at a few fixed points. For example, we say that, okay, after 30 epoch, we reduce the learning rate by a fixed amount of value. So for example, for redness, we multiply the learning rate by 0.1 after every 30 epoch, right? And by multiply with 0.1, we actually reduce the learning rate by 10 times, right? And this could be the visualization when you visualize the loss. And you see at the 30 step, you see a big reduction in terms of loss, right? Okay, we can use the cosine rate decay, and it is actually here's the formulation for the learning rate. So the learning rate as the time step t equal to 1/2 initial learning rate, and then this is a cosine function, right? And the shape for the learning rate is this, the curve, this blue curve, right? And we can use a simple linear rate decay, and this is the actual formulation for for reducing the learning rate. The initial learning rate multiplied with 1 minus t over t upper. T upper is upper t is the total number of epoch, and the small t is the current time step, right? And we see this is a curve. It's a line for the learning rate. We can have inverse square RT, a total number of epoch, right? And this is a formulation. And for this formulation, this is a curve for the learning rate over time, right? We can use linear warm-up schedule, such as in the beginning, we can configure to have a high initial learning rate, right? So we use high learning rate with the purpose to make the model to have the way to explode, right? To explode a different direction in the log plane, right? We linearly increase the learning rate from 0 to the first 5,000 iteration. This is a mechanism we can reduce the explosion of the rate at the beginning, to increase the rate gradually for the first linearly for the first 5,000, and then we start reducing the rate again. So we have an empirical rule of thumb. If you increase the batch size by n, also scale the initial learning rate by n, right? Okay, so now we discuss the anti-overfitting techniques. So for the training, for model training, usually we care about the training error or the training loss, right? And if we have a good optimizer, good training mechanism, we can somehow reduce the training loss, right? So we can reduce the error of the predicted value in comparison with the graduate's value. But somehow we really want to use that model after the training in production, so that we care about the accuracy during the test and during the deployment in production. So for example, we may see this particular situation. This is the accuracy for the train and the validation validation set. You see that maybe during the training and after another number of iteration, you are seeing that we have the increasing model performance in the training set, right? It keeps getting better over time, right? But the overall performance for the validation set get increased slowly, right? And that is something we really don't want to get, right? We want the model to be good in both the training set and also the validation set and then the test set, right? So now we discuss the way to reduce the gap between the performance in the train and the performance in the validation set, right? So for example, we can use this is a very simple thing to do. Its name is early stopping, right? So the early stopping means that we can stop training the model when the accuracy on the validation set decrease, right? Or we can train for a long time but always keep track of the model snapshot that work best on the validation set, right? Because for example, this is something we might receive when training the neural network. This is iteration, right? And this is the accuracy of the model. If we continue training, we can have the model, the performance for the training set increase, right? But somehow for the validation set, it get increase also, and then at some point getting to be gradually decreased. And in this case, we may explain that the model getting to the point of overfitting to the training data, right? It's getting better for it, getting to be good for the training, but not for the validation data. So we can say that, okay, we can stop here, not trying to overfit the model with the training data anymore. Okay, so we can use other mechanism. Is the regularization, and by using regularization, we actually add some term to the loss, right? We have the loss function, and then we add some term to actually regularize the space that the model would employ during finding the weight, right? We have common regulation such as the L2 regulation. We add this amount to the loss. L1 regulation, we add this amount to the loss, and we can use elliptic list. This combination of L1 and L2, and this adds the amount to the loss, right? And by using that weight, we can help somehow, scope reduce the exploratory space for the weight, right? For example, here, if we use the L2 regularization, we don't want to, we don't want the model to learn the big weight, right? Because it will add data amount to the loss, right? Okay, so another mechanism is dropout. So this is very useful mechanism and easy to use for training the neural network. The idea about the dropout is as following. In a forward pass, we randomly set some neuron to 0. We that drop that neuron out of the network, for example, right? And we have the probability of dropping the neuron. For example, we can use 0.5 as the probability. So in the forward pass, for every neuron, it have a 0.5 probability of being dropped out, right? And if we are doing like this, for example, here is a network after the dropout, and you see some neuron was disappear, and we actually remove the connection to that disappear node, right? And now we have the configuration for the network, right? Okay, so here's the code using the dropout in a 3-layer network. Okay, this is the probability for the dropout, and so this is what is about the S1. Okay, so this is that this is a value function, right? And this is a net input, right? And then the U1, this is okay, this is first dropout mask, right? and then we multiply the S1 with the A1, and actually we apply the mask to the output to the S1 here, and it's actually performing the dropping, right? And then we have the S2 is the ReLU over this net input, and then we have a second dropout mask, and then we have the output is a multiply of the W3 and S2 and plus the bias 3. And okay, so it's very simple to use a dropout, right? Okay, so for the dropout, it have very nice dropout effects. It actually forces the network to have redundant representation, and it prevents co-adaptation of future. For example, assume that we have the network like this, and after the training, we assume that the neuron in the network will learn different property, different feature of the predicted label. For example, this neuron will predict if the input emit have an ear, and this neuron will predict if the input have a tail. This neuron will predict if the input is furry, it have cloud, it have mischievous look, right? And the dropout means that we can somehow drop the future, drop the neuron, and drop the learning feature by that neuron, and still forcing the model to understand that, okay, this is a cat, right? The dropout mechanism can be seen as the way to create a large ensemble of model that share parameter. Because for different forward path, we have different dropout neuron, so that we have different network configuration, but of course they are sharing the parameter, right? We can see that a binary mask is one model, right? And for example, in the case that we have an FC layer with these 4096 neuron, so it have 10 power this big number possible masks, right? So you see that we actually creating a very large number of different neuron, right? But they are sharing the parameter, and by training the different neuron configuration, we actually training multiple different a massive number of neuron. So it's like we have the ensemble effect for the model, right? So during the training, of course, the application of dropout is very simple. But now we want to discuss about the testing phase. Dropout makes our output become random, because now if we do nothing, then somehow we enable every neuron, and then we fed the input, and then of course the output will be somehow unexpected, right? So now so in order to have the correct predicted output, we want to actually average out the randomness at the test time, right? And somehow if we do the correct, average of every randomness, every possible randomness, then we need to do the integration, and this is somehow hard and costly to do. So we can, for the test time, we can somehow approximate the integral, right? So let's consider a single neuron. In this neuron, we have two input. Okay, this is neuron A. We have the input X and Y, and we have two weight W1 and W2. At the test time, of course, we have the output is W1X plus W2Y. But during the test time, we have that dropout probability. So that the test time it is 1 over 4 this. In this case, it is probability that we don't drop, we drop nothing. And this is a case we drop the W2. This is case we drop everything, and this is case we just drop the W1. And then we have this this formulation: 1 over 2 W1x plus 1 W2y. And in this case, of course, we can see that we can approximate by multiply the output with the dropout probability. So as the test time, all neurons are active always. So we must scale the activation so that for each neuron, the output at test time equal to the expected output at the training time. So we actually multiply with the dropout probability. So here's the predict function. We have x1, and then we multiply that with the probability of dropout probability to scale the activation, and also for the x2 we multiply with the dropout probability p, and then again we have the output y. Okay, so to summarize about the dropout, we drop the neuron in the train time here, and in the test time we scale the activation output, right, with the dropout probability. And this is the approximation, right? So if we don't want to multiply the output with the dropout probability during the test time, we can actually do the inverted dropout. Here we divide the output with the p, and then during the test phase we don't need to multiply with the p again. Okay. Any question for this part? Okay, then I suggest that we might take a 10-minute break and then we will continue. Okay, so let's continue our lesson. Okay, so now we discussed a bit about data augmentation. So actually, here's some augmentation for using the for working with the image data, right? And for example, here's the horizontal flip of the image. You have the table, the image, and then you can transform the image by doing horizontal flip, and then you have a new image, right? It's actually a flip of the original one, and then now by doing the horizontal flip, you double the input data set, right? Easily can have a double input training set, right? And you can also use all the transformation such as a random cross and scale. For example, here we discussed about the redness. They for training the redness, they actually pick a random L in the range, in this range, and then they resize the training image with the source size equal to L, and then they sample the random 224 for pass, right? So by doing this, you can actually have a lot of input image with the same label. For example, here you can have multiple images of the cat, right? To train the model to predict this was a cat in the image, right? So that was the transformation in the training, and in the testing, they average a fixed set of crop image, resize the image at 5 scale, and for exercise they use 10 small crop, right? Okay, auto transformation could be the color register, such as the randomize the contrast and brightness of the image to have a new one. And then of course this new one have the new have the same label as the original one. And there's also auto transformation, such as the you can steer the image in for example in the X direction. You can stretch the image. You can doing the land distortion, right? Okay, you can go crazy with different type of transformation that you might think about, right? This is a nice idea to mix up. For example, if you want to predict the image with the to be a cat or a dog, right? And you have two label, cat or dog, right? And usually for that you have the binary label, either it's the dog or either it's the cat, right? And now you can be blind a little bit to mix up the image and saying that, okay, you combine one image of cat and one image of dog, and then you blend the piece of two images, and then you're saying that, okay, if I keep the percentage to be 50-50, then the label for the new image would be 50% cat and 50% dog. And it's our example here, we have a 40% cat and 60% dog, right? So in this case, you can increase the training data a lot by using this mixing up. And of course, by practice, I've been seeing that doing the data preparation like this can boost up the performance of the model a lot. Okay, there's some other library we will try. For example, the augmentation. I use this one quite often for working with the image. You can use image aug, and I did an augment this one. Okay, so try out all these to find the one that is convenient for your choice, right? Okay, now we discussed more on the, I think this is the last topic, right? It's not the last topic, but okay. The topic on choosing the hyperparameter, right? So hyperparameter for the neural network could be the network architecture configuration, the learning rate, the parameter in the learning rate train strategy, or the parameter on the optimization algorithm. Right? You see, in the beginning of the class, we discussed about the decay rate, about the bias, right? Yes, so the control coefficient L2 with decay or drop rate, whatever the hyperparameter. So people usually refer hyperparameter tuning as you are working with the it is like the music. It is the DJ, right? The DJ, right? It's like the DJ in the music. Okay. So you have two common strategy to find out the optimal hyperparameter value. For example, you can use the grid layout. In the grid layout, you can define the different value for different parameter, and then you, of course, if you have different value for different parameter, then in this case you have a grid of different combination of the parameter. And what you can do is that to try out different configuration in the grid layout like this one, and then you can pick the best one overall, right? And in the other case, you can have a random layout. So in the random layout, you may, try to, test different value for the hyperparameter, and the value for the hyperparameter is choose randomly. Right? So in this case, you don't fix the value to average, but you choose the value by random, and then you have the random layout to do hyperparameter tuning, right? In practice, I think that you can choose between the two. If you are sure about different parameter value to try on, then you may start with the grid layout. In the other case, if you have no or little clue on the parameter value, and then in that case you can try to use random layout, right? Okay, so now the ensemble method to combine different model in order to put up the performance of your model, right? And the idea about model ensemble is to train multiple independent model, right? And then at the test time, you average the result of different model, right? And then people saying that by doing that, you may enjoy 2% extra performance than using a single model to predict, right? By doing the average during test time, you may take average operated probability distribution and then choose the accurate mark, right? Okay, so for the neural network, you may instead of training different neural network configuration, you may think about using different snapshots of the same network during the training phase, and that might also be an example of model ensemble learning in neural network. For example, in this case, we can have different snapshots during training. You train the model in a number of iteration, right? And you can decide that at a point in time you can launch a new training from that snapshot at a specific point in time, right? And then of course in that case you still have the model ensemble effect. Right. Okay, so now the last mechanism for training neural network is transfer learning. So for transfer learning, you usually use a pre-trained model that was trained on a big data set, right? And then start from that pre-trained model, you continue fine-tuning the model for your specific data set. For example, normally you start for the image classification, for example, you may start with the model that was trained on the ImageNet dataset. And then you may start with that that model with the learn parameter, learn weight in the network. And then you can say that, okay, I will freezing all the layer, right? So that I can reinitialize, or I can remove the fully collected layer, the last layer here, and replace it with the fully collected layer that is appropriate to the number of output class. And then I can continue training. And during the training, because the paradigm here is freezing, so that it will not be trained. So you only training the fully collected the weight in that fully connected layer in here. So in this case, you assume that the output of that pre-trained model here is the good embedding for the input, right? So this case may work for the case if you have very small or little data sets to fine-tune the model. In the case that you have more data, a bigger data set to train on, then you can freeze a smaller number of layer in the beginning of the network, right? So for example, in this case, you freezing this layer, and then you unfreeze the layer, so you have more parameter to learn, right? Okay, so this is just I mean some recommendation for you to transfer learning. So you consider if you have a small data set, or if you have if you have a similar data set, or if you have very different data sets from the data sets where the pre-trained model was training on. And it is a case when you have very small data set, and it is a case when you have a lot data sets, right? So if there is a data set you have is very small and they are very similar, then you can do a simple transfer learning that just to replace the linear classifier on top of the layer on the top layer, right? Then you can fine-tune it, it's fine. So in this case, if the data is very similar, but you have more data, then in this case you can unfree more layer at the top, and then you can fine-tune, right? In the case where you have very little data and the data is at a very different domain. For example, the data here is about the ImageNet data. They train the pre-trained model on the ImageNet data, and now you need to predict the X-ray image, for example, and you have very little X-ray image, and in this case you are in trouble, right? So in this case you have a lot of data and very different data sets, and of course you can fine-tune a larger number of layers. You won't free from the top to the layer that you might think that it's a good place to unfree the weight in the neural network. Okay, also tip and trick, you might check the link I put in the slide and also in the material folder I sent to you, and also you can check the cost from Stanford, right? Okay, so do you have any question?
Can you explain the transfer learning again in Vietnamese, please? I didn't get it.
You don't get it? Okay. Cái tức là về cái việc mà học transfer learning này ấy, đúng không? Thì ý tưởng tức là gì? Chúng ta sẽ lấy một cái mô hình, một cái mạng neural network với các trọng số mà đã được train trên một cái bộ dữ liệu có sẵn. Ví dụ là thường được train trên một cái bộ dữ liệu lớn có sẵn với những bộ rất là phổ biến. Ví dụ là nếu em làm cái dữ liệu ảnh chẳng hạn, thì em có thể start với các cái mạng neural network mà đã được train với cái bộ ImageNet, đúng không? Thì sau khi mà em lấy được cái pre-train network ấy, tức là cái neural network, ví dụ cái RedNet chẳng hạn, đúng không? Thì em có cái RedNet đấy rồi, và các cái trọng số của cái mạng neuron đấy thì nó đã tức là đã được train rồi ấy. Tức là những cái trọng số trong đấy thì nó đã đảm bảo rằng là ok, là bây giờ là em đưa cái input vào, đúng không? Thì em sẽ có thể lấy được output, và output đây nó sẽ là gì? 1 trong 1000 nhãn của cái bộ ImageNet chẳng hạn, đúng không? Đấy, thì bây giờ là em cũng có một bài toán là em phải phân lớp ảnh, đúng không? Thì bây giờ em có thể là gì? Thay vì là em phải tạo ra một cái mạng CNN ngay từ đầu, và sau đó là em tiến hành em train cái mạng CNN này với cái dữ liệu của em, đúng không? Thì em có thể nghĩ đến cái việc tức là sử dụng transfer learning. Thì em vẫn là cái bài toán phân lớp ảnh thôi, đúng không? Nhưng mà em thấy rằng là gì? Em có thể tái sử dụng được các cái trọng số ở trong cái bạn RedNet mà người ta đã học được khi người ta train với bộ ImageNet. Tại vì trong cái mạng CNN, đúng không? Trong những slide đầu tiên mình nói rồi, đúng không? Em có thể hình dung là với cái mạng CNN, đúng không? Thì thường các layer gần đầu, đúng không? Thì nó học được các đặc trưng gọi là đơn giản. Các cái layer đằng sau, đúng không? Thì nó học được các đặc trưng phức tạp. Thì với bài toán phân lớp ảnh thì rõ ràng là gì? Những cái đặc trưng đơn giản thì có thể là gì? Nó sẽ giống nhau, đúng không? Không cần là gì phải học lại. Thì chúng ta có thể tái sử dụng. Thì cách tái sử dụng tức là gì? Chúng ta sẽ lấy cái mạng RedNet đã train rồi, và sau đó là gì? Trong tình huống này là chúng ta sẽ có thể là xin lỗi, để tôi quay lại cái slide. Trong tình huống này là chúng ta sẽ có thể là đây, chúng ta sẽ bảo rằng chúng ta sẽ đóng băng tất cả các cái layer này, trừ cái layer cuối cùng, cái layer fully connected layer C này, tức là cái mà theo dạng là để mà phân lớp ra một cái ảnh xem là thuộc bao nhiêu nhãn đấy, đúng không? Thì FC 10.000 này chẳng hạn, đúng không? Bây giờ tôi sẽ có một ảnh, cái bộ mới của tôi là nó không phải 1000 nữa, mà nó chỉ là 10 lớp thôi chẳng hạn. Thì tôi thay thế cái FC này bằng cái FC 1000, cái layer cuối cùng bằng cái FC C này, và tất cả các cái trọng số còn lại thì tôi đóng băng, và tôi sẽ là gì? Khi mà tôi train ấy, thì tôi sẽ không cần cập nhật các trọng số cho cái phần này nữa, tại vì tôi hy vọng rằng là gì? Cái output sau cái là gì? Cái FC 4096 này nó đã là thể hiện một cái vector 4096 chiều, nó là cái embedding của cái ảnh rồi, đúng không? Và tôi giờ chỉ là học một cái hàm để phân lớp xem là gì, với cái ảnh đầu vào, đúng không? Qua các layer này tôi được cái embedding là một cái vector 4096 chiều, thì tôi sẽ là gì? Phân lớp nó thành là gì? Một trong các nhãn C, đúng không? Tức là em sẽ hình dung rằng là gì? Em đã là gì? Khai thác được là gì? Cái embedding từ một cái ảnh ra một cái không gian embedding 4096 chiều bằng cái việc là em sử dụng một cái mô hình phân lớp ảnh đã có sẵn mà nó đã được train trên cái bộ là ImageNet. Em hiểu ý tưởng chỗ này không?
Dạ vâng, hiểu.
Rồi. Thì trong tình huống sau mà nếu mà em có nhiều dữ liệu hơn chẳng hạn, thì lúc đấy thì em có thể cân nhắc là em unfreeze nhiều layer hơn. Tức là lúc đấy khi mà em unfreeze nhiều layer hơn thì em hình dung rằng là gì? Em sẽ chỉ giữ lại những cái phần mạng nữa, cái phần tầng layer ở phía đầu thôi. Tại vì lúc đấy là nó học các đặc trưng đơn giản. Còn những cái tầng phía đằng sau, đúng không? Thì em muốn là train lại để là học được các đặc trưng mà phù hợp với bộ dữ liệu của em. Ví dụ trong tình huống này là em giữ lại toàn bộ các cái layer CNN, và em retrain lại toàn bộ các cái layer fully connected layer này. Còn trong tình huống khác em bảo rằng là em muốn giữ lại cái tầng này cũng được, mà tất cả các cái kể cả CNN cái tầng cuối này em retrain cũng được, không vấn đề gì cả. Thì cái này là theo cái kinh nghiệm và theo cái trải nghiệm của em thôi.
Dạ vâng, em hiểu rồi.
Ok rồi, còn ai câu hỏi gì nữa không nhỉ?
Em thèm hỏi một chút ạ. Cái trường hợp mà em dùng transfer learning ạ, thì nếu như mà cái dataset của em nó có cái mean và cái standard deviation nó khác đối với cả cái initlet ấy ạ, thì việc em chuyển tức là em sẽ chuyển tất cả cái dữ liệu của mình về cái standard với cả mean của initlet ấy, thì nó có rủi ro gì xảy ra không ạ?
Mình thì mình nghĩ là nó không có rủi ro gì cả. Thì đấy là cái việc em tiền xử lý dữ liệu thôi đúng không?
Vâng.
Mình nghĩ là không có vấn đề gì xảy ra đấy cả.
Dạ vâng, em cảm ơn thầy ạ.
Ai có câu hỏi gì nữa không nhỉ? Hello.
Thầy giới thiệu qua về cái double descent được.
Double gì nhỉ?
Cái double descent nghĩa là nếu mà nó có rất nhiều tham số thì nó sẽ không overfit được cái tập trên.
Em đang nói về cái kỹ thuật gì nhỉ? Mình nghe không rõ lắm. Double descent á?
Đấy không phải là cái kỹ thuật mà là chỉ là một cái hiện tượng.
Em nói tiếp đi, mình nghe thấy có vẻ không rõ lắm em ơi.
Em cũng không biết nói như là đại khái là nếu mà cái mạng của mình nó có rất nhiều tham số thì khi mà train thì trong cái tập valid cái loss có thể tăng, nhưng mà khi mà mình tiếp tục train thì nó sẽ lại giảm tiếp.
Ok rồi. Tức là ở đây em nói đến cái việc tức là mình sẽ chọn một cái mô hình mạng mà có cái kích thước như thế nào cho nó phù hợp gì?
Em nghĩ là như bạn đấy là kiểu bình thường nếu mà một model mà chúng ta xảy ra overfit ấy, thì ở trên cái test accuracy nó sẽ bị giảm xuống. Tuy nhiên nếu mà chúng ta cứ tiếp tục tăng cái độ sâu của model ấy lên thì đến một mức nào đó cái số lượng parameter nó đủ, thì cái đó thì nó sẽ không có xảy ra hiện tượng overfit nữa, mà ta cứ trên mãi thì cái test accuracy nó cứ tiếp tục tăng lên.
Em có cái hình vẽ mô tả ở đây không?
Theo em nhớ thì nó là gọi là cái gì, mô hình thuật toán hiện đại ấy. Nó khác với cổ điển ấy. Không nhớ lắm cái gọi là cái gì.
Nhưng mà trong tình huống đấy thì rõ ràng là em đang trên một cái mạng mà cái kiến trúc của nó có sự thay đổi.
Thầy đợi em một tí để em tìm cái ảnh chủ thị.
Khánh thử kiểm tra xem tớ gửi vào cái chat này đúng không?
Ok rồi. Test with line, set with curve, contour. Ok, tức là em đang muốn nói tức là một vài các cái tức là một vài các kiến trúc neural network đúng không, mà nó có bị cái hiện tượng double descent này, tức là khi mà chúng ta đây là chúng ta tăng cái kích thước của mạng lên, thì ví dụ là trong quá trình chúng ta training thì nó gặp tình huống tức là cái loss ứng với training set thì nó liên tục giảm, nhưng với cái test set thì nó sẽ lại thì có thể là có một lúc nào đấy nó tăng lên và sau đó thì là gì, nó lại giảm xuống, đúng không?
Dạ vâng ạ.
Thế thì cái câu hỏi của em ở đây là gì nhỉ?
Em muốn thầy giới thiệu về một cái này.
Cái này thì thực ra mình lại không chưa từng tìm hiểu về cái này nhiều lắm, nên cơ bản là mình cũng sẽ không có nhiều chia sẻ với em được. Mình đang thấy là cũng có nghiên cứu người ta tìm hiểu về cái này rồi, thì nếu mà cần thì mình có thể là mình xem qua một chút, nhưng hiện tại thì đúng là mình sẽ không có chia sẻ gì được về vấn đề này.
Dạ vâng, em cảm ơn thầy.
Còn ai câu hỏi gì nữa không nhỉ? Ok, thế chúng ta nghỉ tại đây nhá. Hẹn gặp lại cả lớp vào tuần sau.
Em thầy.
Bye
Chào
bye.
thầy ạ.